Hello, this is Jennifer Dassinger with A Plus College Ready, and I'm here to go over with you today the first set of notes in our three-part series of Unit 5, Atomic Properties and Bond Basics. So let's begin. What is a chemical bond? And a chemical bond is an attractive force that holds groups of atoms together that make them function as a unit. Okay, so it's a force. Bonding relates to physical properties such as melting point, hardness, electrical and thermal conductivity, as well as solubility characteristics. Why is this so important? We always look at the energy. Remember, the force. The energy flows through everything. So bond energy is the energy required to break a bond. Now, this is a huge misconception that is out there in terms of students getting this backwards. Energy has to be released, aka exothermic, when a bond is formed. Therefore, it requires energy to break a bond. Not make a bond, but break a bond. Energy is required to break a bond. And once that energy is required, you go to the lowest energy level. For example, we want to be in bed all day. Okay, so here's our three types of chemical bonds. Our first type of bond is ionic. And in the diagram up at the top, you see that the attractive electrostatic forces of the two ions. The cation of the sodium, notice the size is much smaller in purple, and the green chlorine atom. And notice the radius is much larger. Notice the spacing between those. We're going to go into a little bit more definition in a few minutes. Covalent is our next type, and of course we have our lovely water molecule over there. And in bonding, covalent bonds, there's two types. There's polar covalent and non-polar covalent. And the definition of covalent, the best one is a mutual attraction of electrons, whether evenly, as in non-polar covalent, or unequal distribution of attraction in polar covalent, such as our water there. If you see, the oxygen is much larger than our two hydrogens. Our third and final type of bond is metallic. And metallic atoms are bonded to several other atoms. It can be like atoms. For example, I have the diagram of gold, and notice that they're kind of not so much in an evenly spaced format, such as our ionic, but they're kind of in a C clumped together. And we'll go more into that in terms of those delocalized electrons. All right, let's go to our next slide. So chemical bond basics is all about the electrostatics. And these are forces called chemical bonds that hold those atoms together in molecules and keep those ions fixed in the ionic solid, as you saw in sodium chloride. These electrical forces, if you look at Coulomb's law, you notice that the electrostatic force is equal to the Coulomb's constant with the electric charge of Q1, and Q1 is a proton positive, and our Q2, which is a negative charge. So you can think of it as a cation and an anion, or proton to electron charge. And as, of course, the distance decreases, that means unlike charges attract. So think about proton to electron. They'll have attractive forces. But if you see like charges repel, the proton to proton force that is in the nucleus will repel each other from one nuclei to another nuclei. And then you will also have, notice, the electron to electron force within that atom and within one atom to another, which will also repel. So if the charges are opposite, the energy will be negative, exothermic. If the charges are positive, their energy required will bring them together and will be endothermic. So ionic compounds create these solid crystals. And if you notice, they align themselves to maximize that repulsive force. So that electron in Coulomb's law, if you notice, the purple ion, which is a cation, is purposefully distributed throughout the crystal lattice, separating it from the other sodium cations and maximizing the space between the chlorine to chlorine. So therefore, you'll create that separation of charge. So you'll have the attractive forces of positive to negative, and you'll evenly create a space where the repulsive forces are minimized, if you notice, between the atoms. And that creates that very stable structure of a crystal lattice. So lattice energy is that energy to change it from a solid compound from its gaseous phase. And this is what helps the energy that goes into making an ionic compound. All right, so ionic compounds tend to react to form noble gas configurations when they bond together. That's why they have the lowest possible energy. And just as a review again, metals will lose electrons to form cations, such as our sodium, as we saw, and nonmetals will gain electrons to form anions, as we saw with our chlorine. Now, the ion size increases as we go down a group. So cations are smaller than atoms they came from, and anions are larger. Across a row, they get smaller and then suddenly larger. Now, this is what we call a periodic trend. It is just a trend and not an explanation. You can think of trends in terms of multiple choice questions, but realistically, the best science for you to know is Coulomb's law. In terms of the attractive forces of the positively charged cation, to the negatively charged anion, and the scale of the radius between them. So think about that electron to proton within the atom itself. So if you're looking at sodium, think about why the radius is smaller there as compared to chlorine. Chlorine has a much larger radius because it's on the same energy level, but it has more electrons within that energy level, and it's pulling and it's more attracted to that proton in the nucleus. When you add more, you have more attractive forces. So why is it not getting smaller? Because of those repulsive forces between the electrons that are being added in that energy level. So think about that Coulomb's force. Think in terms of attractive forces and repulsive forces. All right, moving on. Hopefully you're not too confused. You can stop the video at any time to review. Metallic bonds, again, notice the diagram. Basically, it's a floating packed cations in the sea of electrons. So they just kind of swarm around, they delocalize. They really don't have a stable structure as much as an ionic bond. Even though they appear solid, obviously no metals, for example, gold, has a low melting point, much lower than salt. So they're not bound to any one individual atom. They're floating around. So we know metals can form alloys, and basically an alloy is just a mixture of metals. And some common alloys, for example, are brass, sterling silver. Sterling silver is made up of silver and copper, and it's harder than silver. Bronze even has copper and tin in it. So those are just some examples of metal alloys. The last couple of properties that we'll be talking about for the rest of our videos will be all about covalent bonds. So now that you have an intro to your types of bonds, again, ionic, covalent, and metallic, we're now pretty much going to spend the rest of our time talking about covalent bonds. Thank you for listening today, and don't forget to practice and review your student notes. Have a great day.